I think. Yeah. Okay, so I think it's time to get started. Welcome everyone again to this final discussion session. And before I just pass the words to the stars, let me just say that, well, first after this week of this live conference and in flesh and blood with many people that we didn't see for a long time, I hope that you enjoyed the diversity of the topics and the many beautiful talks we had. And I think it's my duty to make this public, which is, so this conference was organized by, as you know, by people here in Nijmegen. But there was a driving force that, was unstoppable and made this conference happen in a rather short notice, which is Professor Frank. So, and I think, oh, sorry. I have to be here, okay.
Science, please.
Just one sentence more. So I think he went really beyond the ISQG, the International Society for Quantum Gravity, and he made a really great job for the quantum gravity community in general. And I hope that, I don't hope, I really felt that this must be emphasized very, very loudly to all of you. Okay, so during the week we collected some questions and from virtual participants, from you, and well, we had a nice collection of questions, but there was some overlap, and I tried to condense as much as possible all these questions in 4 questions, and I'm sure that we're not going to discuss the 4 questions, but I think I will start with the one that I selected as the first one, and the format will be the following. Every panelist will speak for about 2 minutes about their view on these questions, and then we open to the audience for comments and discussions. So the first question was a combination of 2 frequent questions that appear in the Google form, which was, in your view, what is the relevance of unitarity in the construction of a theory of quantum gravity? And in particular, what is the meaning of unitarity in the context of quantum gravity? And just a plus, which is very much related, I think, what is the relevance, if any, of solving the so-called black hole paradox, the information loss paradox, for our understanding of quantum gravity? So with that, I shut up and give the words to the panelists. So, is there any order that we should respect? Okay, let's do left right. Okay. Okay. So, Jan.
Yeah, those are all very interesting and complicated questions. For me, what's important is that I think a minimal ingredient for quantum gravity is that semi-classical gravity emerges in a suitable limit. That is described by the usual action and everything. And the minimal approach to that is that it's just some sort of low energy effective action. We can be somewhat agnostic what happens at the high energies, but it's supposed to be a very good low energy effective action even at the perturbative level. So all the notions of unitarity and locality and so on that apply to perturbative low energy effective field theory should come out of any approach, I think. Whether or not there is a notion of unitarity in a full non-perturbative completion is a much more confusing question. Because maybe it's trivial, like if you just take the Wheeler-DeWitt equation as it stands, it says that H psi equals 0. That means there is no time evolution, and in particular there is no interesting notion of unitarity whatsoever. If you look at the ADS-CFT, where you have a boundary then unitarity is sort of built in because the boundary field theory is unitary. So it really might depend a lot on the precise setup, what actually the non-perturbative version of the question is. But at a minimum, I would say it's a very important thing is that all the unitarity properties of perturbative gravity should be reproduced by any approach at low energies.
Yeah, I guess Jan got it covered.
That's too easy.
So indeed, I'm coming from the fully non-perturbative approach. For me, then the question is unitarity does assume some time evolution, but I don't usually know what is a notion of time. And so if I don't have a notion of time, how can I define unitarity? But of course, I want to reconstruct unitarity in the low energy limit, in situation where I can have a good time, in situations, for instance, in which I'm asymptotically flat, or have a boundary. In addition, there's kind of two recent questions which you can consider. One thing is if you do have if you do believe in some kind of fundamental discreteness, but we also do have an expanding universe, you might ask how that goes together. And Philipp Höhn and myself have developed such a formalism, but also recently have been a paper by Strominger and Kotler about weakening unitarity. It becomes even more paradox if you think of collapsing universes and lots of information. So there's this thing. The other thing which I'm reported in my talk is these complex terms in the action for topology change. So if one thinks about topology change and third quantization, which Daniele spoke about, it's also lots of questions for me. What does unitarity mean in this context? And for what do we need it? I mean, usually we need it for probability interpretation, and there are some frameworks which try to generalize this probability interpretation and to have generalized quantum mechanics. So it's also kind of a question, do you want to reproduce exactly the quantum mechanics, or do you expect some modification of quantum mechanics from quantum gravity?
Partial coverage, but let me add my own point of view, which comes from also very much informed by non-perturbative theory, where we're working in a framework where one can, we have some quantitative understanding already of mechanisms of emergence of anything, which I would say these are the kind of the basic principles. I mean, I wouldn't just name unitarity, but also locality and causality, which I would say people, of course, say, oh, anything goes at the Planck scale. But then, of course, it has to be regained, or to use the more popular term, it has to re-emerge. And things typically just do not emerge, because by what mechanism you have to ask? I mean, wishful thinking alone is not enough. You know, you have to come up, even, you know, try it in toy models, this is very difficult. So you abandon these principles at your peril. So if at any lower energy, you know, even be just where gravity is completely switched off, of course, I mean, unitarity is very much built into how we think about, you know, standard quantum field theory. So I think, so that's point number one. So as a corollary, anyone who loves and strongly believes in Euclidean, you know, in Euclidean quantum gravity also has to explain where, well, how does time, you know, re-emerge? And therefore, how can I even start asking questions about unitarity and causality? To the issue of, oh, you know, part of my heart is canonical, so, oh, there is this problem of time, and which time should I choose? I would say, well, choose a time and show with respect to that time, make it natural, make it proper time, make it cosmological proper time, or, you know, something that's not just some coordinate time you picked out from, you know, an infinity of possibility, and show unitarity there. I think we know that it's asking too much to have all time reprogramatizations unitarily represented in some non-perturbative theory of quantum gravity. I think this is wild. So try and make things unitary. Of course, there are hard questions when you come to cosmology, but I'm just talking in the sense of more well, quantum gravity, after all, is something like a local quantum field theory, hopefully.
Okay. Well, I'm a student of Bryce DeWitt's, and Bryce always said that you should push what you know as far as you can to see where it breaks rather than throwing it away. So I'm reluctant to throw away something that seems to be a very fundamental part of quantum theory as we now understand it. That being said, though, unitarity, as other people have said, refers to time, and in order to say whether it makes sense in quantum gravity, you'll have to tell me what you mean by time. In settings where, like ADS-CFT, where there is a clearly defined boundary time without quantum difficulties, then I think unitarity is very natural in terms of boundary time. Though even there, it's not clear what bulk unitarity means. In a more general setting, if you want to use some kind of relational time, you would have to tell me what that time is. Is it, even classically, is it defined globally? Is it defined for every manifold that you might want to include in a path integral? If you can give me a relational time like that, then I would expect something like unitarity, or at least that would be my first guess. I don't know that such a time exists.
Okay, I think unitarity and the question of black hole information, really are together key questions in the field, so much so I suggested a more substantial discussion on it. Maybe whoever organizes the next quantum gravity might go more in that direction. The reason is as follows, without a complete discussion. If we consider the alternatives, some form of non-unitary evolution, we typically land on a disaster, basically. It doesn't work. On the other hand, if we try to preserve unitarity in the black hole context, we get strong indications of new non-local behavior of quantum gravity. So it seems to be telling us something. And that's why some of us view this as a key problem for quantum gravity. So without going into all the details of that, let me just mention one other point, and I think it's also sociologically important in the context of black holes, because we can talk about one or the other formalism of gravity and what's better about it, et cetera, but really focusing on what different formalisms have to say about specific physical phenomena, Gedanken experiments and so on, gives us an opportunity for more concrete dialogue between different ways of looking at things. So those are at least two of the reasons. And finally, regarding whether unitarity is sharply formulated, I agree when you try to think about, say, finite time evolution, there are various subtleties. But one sharp way to think about it is if the theory of quantum gravity has states which behave like asymptotically flat space, Minkowski space, then you can think about the S matrix and ask about unitarity of the S matrix. Of course, you have to deal with subtleties of infrared issues, but there very much you can make it a sharper question. So that's it.
Thank you very much. So now we open the discussion to the audience. So I expect that some of you would like to kick off either asking the panelists or raising another concern about unitarity. Okay.
Thanks. As a former quantum fundamentalist, I'll try to maintain two contradictory ideas at the same time. I believe that unitarity is important and it was covered, as we say here. On the other hand, I'm not sure that information loss problem and unitarity in the context of black hole evolution is really significant issue. It's very useful in prompting people to think about a number of topics, and I think some of them are very important. But if you say, from the standard of formulation of standard quantum paradox, if we try to formulate what goes into clean formulation of information loss problem, we end up with a list of important questions, particularly about nature of degrees of freedom of a gravitational field and how it translates into quantum domain and whether they're local or not. But we are far from clean formulation of information loss problem. So in a sense, I don't believe it's a problem. There is a long list of things that need to be precisely defined for us to honestly declare that we have a problem. But unitarity is important, and whether it's true or not, above my pay scale, but it's an interesting and useful tool.
Okay. Perhaps, yeah, should alternate. Otherwise.
So, I mean, one question to me is always, given that unitarity sort of breaks down in every single measurement, why should we believe that it holds as a fundamental assumption in large, like in the theory describing the whole universe? So, like in my point of view, it's sort of like the worst assumption in fundamental physics because it's violated in every measurement, and the connected question would then be, can we solve quantum gravity without solving the measurement problem?
Do the panelists want to say something about that?
The statement that it's violated in every measurement depends on a particular view of what a measurement is, and so I don't think that's a fair statement. If we think about the full quantum evolution of the universe and observers in the universe as quantum systems, then that's not really how we look at it, and say decoherent histories or something. And again, regarding the sharp formulation, one reason why we can think about it, this comes back to the first question, or why we should think about it, say in terms of the S matrix, is there we have a kind of clean formulation in terms of asymptotic states we think we understand. Ordinary particle states coming in or boosted versions of those, going to ordinary particle states going out, and you can cleanly formulate it, again, modulo some IR subtleties in that framework. And then, you have a leading semi-classical contribution to those processes in the ultra-high energy regime. And based on Hawking's analysis, that leads to a disaster, a huge amount of missing information. And so, I think when you look carefully at what goes into it, there are not so many subtleties as were just alluded to.
There is a
Okay, this is just to spark more discussion on this issue. We could go for longer, probably. I didn't like this way of starting, saying that once you give up unitarity, everything is a disaster. Why? Because it disqualifies every possibility before giving any reasons. In a sense, for me, in a quantum gravity conference where we are talking about space-time things, it's a little bit disconcerting that we are talking about an issue that when we want to ground it, we have to say about things about the S matrix, where things evolve only in time. So in a sense, we want to make things space-time local, and they're talking about unitarity as a building block is very restrictive. So I don't want to claim I have answers, but I'm saying that if we put it in as a requirement, we are tied to something very, very strict. I like much more the point of view that it has to be recovered somehow in certain limits, and to, for example, when we analyze the S matrix, yes, it makes sense, and there is something we have we have a reference, and we can say we want to conserve probability with respect to that thing. But in some other aspects of what we want to talk, we have a local theory, and we can say we want to preserve probabilities of certain things with respect to certain other things. And anyway, that's my point of view, just to spark more discussion.
Hi, just to give an answer to the question of that guy. Well, I'm not a specialized people, but there are some groups, especially in my university, that they think that actually we cannot solve the problem of quantum gravity if we do not solve the problem of the measurement problem in quantum mechanics. They believe that these two things are very strongly connected. So actually they have some words where they relate the measurement problem with the information loss paradox. So, and in some sense, I agree with them that we need to be more careful, especially when we talk in some technical aspects of our approaches. It is important to, yes, to clarify that technical aspects, but it's also important to clarify some conceptual things like this one, because if we are not able to clarify that questions, we will be in trouble because maybe we are doing something that is not right. So it could be very important to clarify these kind of questions, and answering to the question of this guy, there are some people that believe that no, we cannot solve the problem of quantum gravity without solving the measurement problem. So there are other perspectives, but I actually agree with them. But answering the question, well, there are people that believe that no, we can't.
Okay, so just to organize a little bit, so Sumati has a comment, and Bianca has a comment, and then we move to other topic. Okay.
This is just to add my two paisa to the discussion, which is that it seems that the broader context of unitarity has to do with probability conservation. And the question within any quantum formulation of quantum gravity, if you think of that as a way to think of unitarity, maybe there are formulations in which we're not talking about evolution being unitary, but that in some broader sense, say in a history's perspective, where you can think of the decoherence functional or the coherence functional, whichever way you like to call it, as giving you a normalization, telling you that in some broad sense, quantum probabilities are preserved. So and in that way of thinking about it, you don't really need a way, you don't need a time, you don't need an evolution, you don't need the sort of local definition of unitarity. So I'm just suggesting that there could be broader conceptions of our understanding of unitarity, which are based more on a history's perspective.
Bianca?
Well, to be on a more reconciliatory note, I think, well, I do think many of us spoke in a global context. We don't know what the notion of time is, what unitarity is, and Steve was talking about more local things and high energy scattering. And there I do think it's a very important question of what happens in a high energy scattering, where you can have a time asymptotically, and whether black holes form, and whether everything is consistent, and it's a question about the stability of even flat space to understand these processes. And I would like indeed to know in the various approaches what the answer is to have ultra-Planckian scattering, whether these are unitary processes or not. I do think that would have been important consequences. So there's probably, two different kinds of answer depending on what kind of processes you consider.
Okay, thank you. So, as I said, we don't have time for all the questions, so I will merge two questions. And the second question is, what are the most promising avenues for experimental hints in quantum gravity? So what or where we should focus our efforts? And merging to the other question, is local Lorentz invariance a potential candidate to be looked at? So now I pass to the... No, so yeah, so it's a question about experimental hints of quantum gravity, and if you have something to add about local Lorentz invariance, that would be good. Okay, so Jan can start.
That's not fair, huh?
Ah, okay. So you want to? Okay, that's fair enough. Okay.
Okay, for regarding local Lorentz invariance, I bring a standard complaint, which is I don't know what local Lorentz invariance is. So if I try to define it, it's for me a version of diffeosymmetry, and so diffeosymmetry I find very important. But then it's a question, indeed, how does it influence the propagation of matter? Well, I would like to have that in a background independent and ideally diffeosymmetric way as far as it's possible. But I can imagine that there's kind of something like a deformation of Lorentz symmetry happening. Regarding promising avenues for phenomenology, I do find currently very interesting these new considerations on basically gravity-matter interactions. That goes a bit also, relates to the swampland, to consider what kind of matter couplings and behavior we can predict or post-dict from the consistency of quantum gravity. And that seems to be, for me, indeed, promising to give lots of restrictions on our quantum gravity theory as far as we can compute it.
Okay, question number one. Yeah, so the local Lorentz, yeah, I agree with Bianca. I think we agree on the same point. If you are in a really non-perturbative regime where there is no G mu nu, even in an approximate sense, there is just no operational way to talk about the action of the local Lorentz group. So that question only makes sense, let's say, for anyone who works with some discrete models or something like DTs or others, where there is no, not even, as I said, in some approximate way, a G mu nu to talk about, where or a local patch of your geometry where, to some approximation, it looks like, a piece of Minkowski space, and then I can start talking about rotation. So I don't think it's like diffuse for me, but it's something like, of course, tangent space doesn't exist if you don't have tensor calculus, but if you have can approximate your patch by, something that looks Minkowskian, then you can start talking about this. It's an important question. Again, how will that emerge? It's part of emergence of space-time structure, I would say, coming from a very non-perturbative point of view. So it's an interesting question. In terms of where can we make contact with cosmology, again, I'm slightly biased by my own constructions and point of view, where we find from CDT an emergent space-time that has some de Sitter properties. So, and the very obvious thing is to compare it to early universe cosmology, where everyone else takes a nice, perfectly symmetric de Sitter space as their, their preferred vacuum state, if you like. So the question is really, can we derive this from first principles, and can we confirm, for instance, by studying two-point functions, that's something it's coming within grasp of what we can do, assumptions that are being made and kind of pulled out of the head, which are the starting point for standard cosmology. And of course, the magnifying glass we have is then inflation that comes after, doing whatever our perturbations are then, coming perhaps from an underlying quantum theory.
Okay. So first of all, when quantum gravitational phenomenologists talk about local Lorentz invariance, I don't think they mean what mathematical relativists mean by local Lorentz invariance. I think they mean Lorentz invariance over large macroscopic scales small enough that the universe is approximately flat, but much larger than what we mean by local Lorentz invariance as a gauge invariance of the tetrad. I think it's worth looking. I would not bet any amount of money that violations of Lorentz invariance are going to be found anytime soon. For promising experiments, well, I'm very excited by these upcoming, maybe 10 years from now, tabletop experiments to see whether entanglement of positions of Planck or larger mass induce entanglements of gravitational fields, because it would be nice to have some actual observational evidence that gravity is quantized. But it would also be totally shocking if any result came out that wasn't what we all expect. I don't know what else is a promising experimental avenue. I think we have to look all over the place. As I said this morning in preparing a review about causal structures in quantum gravity, I realized that this may be my own ignorance, but I don't think that enough attention maybe has been paid to the question of whether even Planck scale fluctuations of causal structure might be observable. But I leave that as an open question.
Okay, I guess I'll address the more formal notion of Lorentz invariance. And if quantum gravity does have a state that behaves like the Minkowski vacuum and excitations about that, then it seems to me that Lorentz invariance itself is a key property in that context and is pretty well tested in sort of this large radius limit as compared to the Planck scale. But then locality is a little more puzzling. So the extent to which we have locality, we will have local Lorentz invariance perhaps, but locality, in my mind, is in question. How to think about that sharply in gravity. And so possibly modifications to locality are a key point here. My own view is that the underlying structure is quite possibly not the geometry of a manifold, and so in a way it's not even the right question, or it's not the right way of going at it. On the experimental end, I guess one could also mention new tests using interferometers, which are more lab-based. That's one possibility. But I also think we should really consider quite thoroughly that we're now observing strong gravity regimes near black holes 2 new ways, right, in the past few years. And moreover, this problem of information loss, this severe problem of unitarity is suggesting that there is, in my mind, quite likely some new phenomenon taking place in that regime at scales of order of the event horizon radius. And I think, in fact, that's in some sense emerged as a consensus of the field, or some part of the field who thinks about this. There have been various proposals for what the new physics is on event horizon scales, but modulo the fact there are different proposals, the consensus is that there is something novel there. And so we should really try to think hard about whether that can be seen via gravitational wave observations or, of course, the more electromagnetic-based observations like with Event Horizon Telescope.
Very good. So as far as local Lorentz invariance goes, I don't have much original to say because I was also confused what it means. If it means the equivalence principle holds locally and so on, then my answer would be the same as for unitarity. We think that perturbative gravity should emerge, and to the extent that that has local Lorentz invariance, it should come out in that way. Any more drastic modification where you by hand, imagine adding a term that explicitly breaks general covariance in an effective field theory, seems to me theoretically poorly motivated at this moment in time. As far as experimental things go, that's obviously a super important question. I think this idea of trying to see whether UV completability of a low energy theory in the spirit of the Swampland program puts bounds on coupling constants, as Bianca was mentioning, is a nice thing to explore. Perhaps looking at density fluctuations in the early universe will shed some light. There's some extra data coming up about what the initial conditions of the universe were. And there might be various ways to try to connect that to quantum gravity somehow. For example, if you think the initial state of the universe was related to some version of a no boundary proposal, then different choices of, say, no boundary proposals or complex contours that you choose for early times might have different imprints on density fluctuations. I kind of sort of intuitively feel that the fact that black holes, when you increase their energy, they also increase in size, is a weird thing, because normally if you increase the energy, you go to shorter distances, not longer distances. This is sometimes referred to as UV-IR mixing. So there might be some connection between physics at very large distances and physics at very short distances. And so it's conceivable that maybe some sort of quantum gravity phenomena that you might naively think operate at the Planck scale, by some sort of UV-IR mixing have very interesting, very long distance effects as well. But I don't think we know precisely how to look for those, but it's an interesting thought. I also think it's maybe like if you think about, say, Aegis CFT, it's interesting to see whether you can just put these CFTs on a computer or, as was recently tried, put some qubits in a lab and try to sort of see if you can engineer quantum, things like quantum wormholes and so on. I mean, this is a very contentious result. But as a general direction to see if this is a way to sort of do quantum gravity in the lab in an indirect way, I think it's also a fun thing to try to do. It's maybe not directly testing quantum gravity in our universe, but it does test in some way some conceptual foundations of quantum gravity. That's it.
So now we move to the audience and comments, questions. Claudio? Okay, so let me give a chance to someone else.
Okay, I just wanted to make a technical comment, a short technical comment regarding this thing about local Lorentz invariance. If you remember the history of GR, general relativity, there was this argument presented by Eric Kretschmann about diffeomorphism invariance of the theory, where he basically said that any theory can be rewritten in a manifestly covariant way, right? So this is the effect of diffeomorphism invariance is really not a physical requirement that you can put on the theory. So the same thing can actually applies to any symmetry. So you can rewrite the Schrödinger equation in a manifestly Lorentz invariant form. So the only issue is that once you do that, you have to sometimes you have to introduce some background fields to compensate for the transformation laws and so on. So basically, what is being done when you say that some symmetry is being broken? what you're actually doing is breaking background independence. So symmetry as such is a matter of convenience of our equations. And background independence is the thing that has content that the physical theory does or does not satisfy. So breaking of Lorentz invariance is actually breaking one specific form of background independence. So.
Okay, thank you.
Am I allowed?
Of course.
Okay, then I would like to pick up on the perspective taken by Jan. So, because this is something where the functional randomization group was able to say something. So you start with something that is diffeomorphism invariant. You add an operator that is non-diffeomorphism invariant at high energies. You try to go to low energies, and then the result was it's not natural that the difference actually vanishes. So I think Benjamin Knorr has a very catchy paper with the title Lorentz Symmetry is Relevant, and this summarizes our take on this question.
Thank you. So, more comments, questions, concerns?
So everybody has been very politically correct, which is good. So that is worth it, and this is worth it. So put a little spice. So what is not worth it?
So I think Claudio wants to make a comment, and
Sorry?
Up there.
So regarding local Lorentz invariances, so I mean there is this recent claim by the VIP collaboration. They are testing the Pauli exclusion principle, and they claim to rule out theta Poincaré violations to order Planck length squared. So any theory basically that requires that is, according to their claim, dead. And I think it does make, you can ask the question of local Lorentz symmetry if your fundamental description comes with an internal space of your degrees of freedom.
Oh, Sumati, yeah. So I see some repetition of faces in the discussion, so we should try.
Just, I mean, in this sort of experiments that have been proposed, there was this question of non-locality as well. I think Stefano Liberati at some point was going to was proposing that there would be tests of non-locality, because that's another feature of quantum gravity that people have talked about. So I don't know this, what is the status of experiments in testing non-locality, I mean, causality preservation without, so not violating causality, but maybe having non-local effects, which can only be explained through a quantum theory of gravity. So I don't know the status of such experiments. If anyone knows, that would be interesting.
If people want to answer to that, otherwise I have another. I just want to add a comment, maybe reinforce something that Jan was saying about UV-IR mixing. Maybe, so my view there is that I think we have to be a bit honest that if you're doing quantum gravity, and if, let's say, Wilsonian decoupling is really at play, then, we are at risk of talking about something which is totally unobservable. So I think as a community, we do have to face that. For me, the only, and I may be wrong, but my view on that is that the only other option is that our theory of quantum gravity, needs to develop a phenomenology which is akin to this UV-IR mixing. So now I think the challenge for us, so maybe you could challenge me on that, and if people have quantum gravity observable, which by that I mean, effective theory is enough. if you have a Wilsonian decoupling, I have effectivity, I put a cutoff, my observation is Planckian, we're done. So now I have my own, reasons to believe UVI are mixing, but in fact, I think it's a challenge for us building models in quantum gravity to kind of see, is there a root? Is there some mechanism like that in the theory we're constructing or not? Or are we proving Wilsonian decoupling? So maybe I'd like to have, reactions on the panel or on the audience, like, where, why our quantum gravity model will be Wilsonian decoupled or UVI are mixed. And if they are not, why are we continuing to work on it?
Sorry? Yeah, just. So, do you want to comment on that?
I could try.
Yeah, and then Aaron has a comment. Yeah.
So, yeah, I could try. I hope I've understood the question properly, but I think the universe has performed scattering experiments that are very much like ultra-Planckian scattering experiments, but instead involving large particle number. And those scattering experiments have yielded some of these things that we're talking about that manifest UV-IR mixing, namely black holes, and very big ones. So, and if we have a complete quantum description of the universe, we'd better give a complete quantum description of those things, basically. So I think it's unavoidable now that we enter this regime if we want a complete theory where we explain quantum evolution of black holes. They're out there, we found them, and you could just as well make them in very high energy scattering experiments in principle if we could perform such experiments. So I'm not sure, does that address your question, or is there some other aspect of it?
Yeah, part of it, that you're saying, yeah, I agree with you that,
So, this was unexpected.
but yeah, I'd also hear from other perspectives.
Just say a few words, and then Aaron takes over, and yeah.
So I don't want to monopolize. I'm happy to hear more perspective on how you. Oh, you have microphone. Yeah.
Yeah.
The theories.
I'll bring them back. But okay, you just wanted. Okay. Okay. I think Aaron wants to say something, and then Bianca say something. Yeah. I didn't know this. Sorry.
Yeah, so I agree with Steve that, for instance, the scattering experiments would be very important to know the answer to. The other is that also if I think non-perturbatively, I have difficulties to defining or deciding what is UV and what is infrared. And as an example, there's this kind of spike, for instance, very spiky configurations, or if you want to have it more drastically, the baby universes, which can have very small diameter and in this sense be UV, but on the other hand, can extend to very large distances. And so that would be part of understanding kind of these phenomena, which are a bit counterintuitive if you are doing standard quantum field theory.
Okay, one comment on maybe terminology to Laurent. I mean, if you call anything that's beyond what we can describe as with effective field theory, UV-IR mixing, I think everyone would agree that that's something we certainly hope for. I mean, obviously we are hoping for quantum gravity signatures, well, which we wouldn't even probably think about if we just stuck to our effective quantum field theories. So that's one thing. Another comment is, I think many people now are talking about, well, conceptual questions and conceptual problems and contradictions as being the real, difficult thing we have to address first. I think that's getting stuff the other way around. I mean, this is what's been happening in quantum gravity for the last 40 years, that people have talked about and argued about these conceptual questions by which they oftentimes mean certain properties of elements in their preferred way to construct or think about quantum gravity. And I think quite a few of those will go away if we focus more on, hey, what is actually now, say maybe even in principle, the operational setup, you know, I would use to show that there's actually a physical effect there. Many of those will go away. So, and of course, one can speculate which those includes. But I think that's a healthier way to go. And I hope also we as a community, we are now more focusing in part, you know, as I was also saying yesterday, triggered by, well, data that are coming in, focusing more on, yeah, this problem-oriented, operationally, you know, what does it mean? Is there actually, there may be a contradiction between my and your formalism, because what I'm talking about is totally ill-defined in your, you know, or conceptually, one cannot even talk about in your formalism, but we may still agree or disagree on the outcome of a certain experiment.
Thanks. I just wanted to comment on what Laurent said about effective field theory, because so first of all, I agree with you. I think that's a possibility that we face and that we should acknowledge, especially to the outside community, that it's a possibility that there's just nothing non-local happening in quantum gravity. But that said, I think there still is some sense of phenomenology, namely, this was alluded already to, consistency with all that effective field theory is something very non-trivial. And I think many approaches have a handle on that, but no approach has a complete picture of that. And I think that should be pushed. And then even in that framework, there's the possibility of a somewhat less exciting phenomenology that can even predict things, right? Because there is some ununderstood stuff even in the effective field theory of our universe. There are open questions, and in the end, in a long way, I think we have something to say about that.
Okay, so I'm quite amazed that after a week of conference, at very last slot is a discussion session, and we still have energy to discuss. But I think in order to, you know, boost a little bit this energy, we should go for coffee. But before we go, Frank wants to say something. But just before Frank speaks, I think we should thank the panelists for the very nice discussion.
Can I go to the slides? So I had the pleasure to make a few closing remarks to this conference. No worries, I will stick to the 5 minutes mark. So let me see. Yes. So picking up the analogies of scientists' fish that we have here, I created a quantum gravity island. And this reflects about my personalized view on the field. So our task is to actually explore this island. So what the island is populated by are many rooted trees with marked nodes. And what we typically do is we live in one of these marked nodes and we want to explore what's going on there. Now I want to thank all the participants of this conference and the plenary speakers and the parallel sessions to give us a scenic view about their particular node on this island. So I think for the community it's incredibly instructive to see and learn what is going on in other parts of your island in order to be able to chart what are the possibilities. Now, you don't organize such a conference alone. So first, I want to acknowledge our financial support. So there were many people contributing. I want to highlight the financial support by Daniele Oriti, so this is the DFG, and also the financial support provided by the Delta Institute and the ERC grant from Jan de Boer. So that makes the conference really a national initiative. And I would have bet my money that something like that would never have happened, but you proved me wrong. So I'm very happy about being wrong about this one. And then there was a huge team being here, organizing everything in the conference. Packing boxes, so that happened before. Then we had a welcome team guiding you here through the Kollegesaal. We had a crew that helped up setting up the posters for the poster session. Maximilian and Jan manned the info desk in the morning for people who registered on Tuesday to Friday. And a particular thanks goes to the audiovisual team, which really made an amazing effort that you could enjoy this conference in a hybrid format. So thanks to all of you on this team. Now I have to say, this is only part one, so I couldn't fit all names on one slide. There are many more. So for our outreach, we also had a team which was guided by Beatrice Bonga. So there was the Science Café on Tuesday evening. This is Eric Stoffels and Femke Verhout. The Study Association organized the walk-in moments for the bachelor students and the master students. So this was Matthijs Lau and his friends. And we had very good outreach speakers talking to the general public and our students here. So also there, a great thank you for all of you. Yeah. And by now everybody has met our secretaries, so they also had a great influence on the success of this conference. Now, in the background, we had a scientific advisory committee. The names are on our website. My apologies if not all wishes of the scientific advisory committee were granted in the program. It was impossible to have all contributions here on stage, unfortunately. Then the International Society, which is running this series of conferences. The Young International Society for having an afternoon session dedicated to PhD students. So I hope that was also very helpful. And then our local organizing committee, Beatrice Bonga, Timothy Butt, Badri Krishnan, Renato Loll, Antonio Pereira. So thank you to all of you. We are still friends after this initiative. Yes, and then of course, the organizing committee stops now, and we are very much looking forward for someone stepping forward to organize Quantum Gravity 2025. So if you are interested in doing so, please raise your hand now, or contact the International Society saying, yes, we are up to this task. So for us, it was a great fun having all of you here on campus, and we all hope that you have a safe journey home. And there will still be coffee in the Science Café where you can say goodbye to your friends. Thank you to everyone.